Hey, it's Mr. Shrum, and welcome back to Physical Science. We left off right before the physical and chemical changes section. So let's jump back in. If you remember from the start of this lesson, we categorized a few examples of physical and chemical changes. Both types have been important to our progress throughout history. The wheel was invented thousands of years ago. Early designs of the wheel involved chiseling wooden planks into thin circular blocks that moved on an axle. This change in the shape and size of wood is a physical change. And another milestone was the discovery and refinement of metals. Most metals are found in an ore form in rocks and soil. Humans have found a way to extract metal in their pure form through the process of smelting. Sounds like melting, but unlike melting, which is a physical change, smelting involves chemical processes that separate metal atoms from ore compounds. Smelting involves a change in the molecular structure of the substances, which is a chemical change. So here we have a cart example, and then the smelting of ore. So let's see how copper is smelted from its ore, malachite. Malachite, found in the Earth's crust, consists of copper-containing compounds and includes oxygen and traces of carbon and sulfur. The copper smelting process involves heating the malachite in fire. That heat breaks the molecular bonds of the copper compounds and removes impurities like that carbon and sulfur. This change is a chemical change. Copper oxides, such as these, still remain in the ore. It is then heated with charcoal at a high temperature in a closed oven, and that produces copper and carbon dioxide gas. So let's watch this video. Let me see, am I sharing computer sound? Yeah, there we go.
Finding pure metal in the ground is rare. Most metals are combined with other elements in the Earth's crust to form rocks.
This is malachite and it contains the element copper, and this is pure copper metal. For thousands of years, people have known how to extract this metal from the rock.
Malachite, otherwise known as copper ore, is found in the ground. This mine here at the Great Orme in Llandudno dates back to the Bronze Age, a time when copper was used for making tools and weapons.
But first, you need to find some malachite.
Underground, there are over 6 kilometres of narrow tunnels.
Where I'm walking now was originally a vein of green malachite. It was dug out by people over 4,000 years ago, leaving behind a maze of passages and chambers. So just imagine this whole cavern was once filled with copper ore.
The first miners used large stones to dig out pieces of the precious green rock. Malachite isn't just one element, it's made of several. As well as copper, it contains carbon, oxygen and hydrogen.
To extract the copper from the rock, you need to get rid of all the other elements, and that's done by a process known as smelting.
First, the malachite is crushed. Then it's placed in a crucible ready for heating. In the Bronze Age, copper ore was smelted in a small furnace made of clay. It reaches temperatures as high as 1,000 degrees Celsius. Of course, they didn't know that in the Bronze Age. They just knew it had to be very hot. Air pumped in through bellows helps the furnace reach the right temperature. Then, in goes the crucible, and it's covered with charcoal. The charcoal reacts with all the other elements in the malachite, leaving behind the copper. And the result, liquid copper, an element. Once the copper has been extracted, it can be poured into a stone mould. It quickly solidifies and begins to take on the shape of an axe head. Its beauty and durability make copper a highly prized element. Today, copper ore is mined on a huge scale and smelted in massive furnaces. Copper metal is used for all sorts of everyday items, like water pipes, coins and copper wire. Tin is another metal element which can be extracted from rock. This is a lump of tin ore. As well as tin, it contains oxygen. Smelted, and once again, the pure metal is left behind. Copper and tin are both elements, so what's the difference between one element and another? Copper and tin are made up of particles called atoms. In pure copper, all the atoms are the same as each other. It's the same with tin, but tin atoms are bigger. A pure element is made of just one type of atom.
All right. So that shows you the processes that are used to purify metals and separate them from impurities, they call them, but they're just other elements. In nature, it's usually a blend of things that you find elements in. You rarely find a pure substance all on its own, and it takes labor and work to derive a pure substance. Chemical changes is, well, we just observed one of them with copper smelting. They turn this bluish green malachite into this red brown metallic copper. Any one of three observable cues typically indicates a chemical change: a transfer of energy, change in color, a new observable product, typically a gas bubbling out or a precipitate forming. We've noted that the color change in copper, so it goes from blue to reddish. Careful measurement also shows that smelting requires energy input. Finally, carbon dioxide is formed, but this gas is hard to observe as it escapes directly into the atmosphere. So you can't really tell that that's going on. So two readily observable cues, the color change and energy input, indicate that this smelting process is a chemical change. So just look out for these cues if you're confused whether it's a physical change or a chemical change. Physical changes involve things that do not change the molecular structure. So chemical changes involve changes in molecular structure, while physical changes do not change the chemical nature of a substance at all. Physical change involves a change in the phase, such as dissolving one substance into another, or the separation of dissolved substances. So think about melting ice. Melting is a physical change that involves only a change in the phase, such as ice to liquid water. Melting does not change water at a molecular level. It remains H2O in both phases. The change in phase is reversible. So for example, when you take solid ice out of the freezer, it melts into liquid water. If you put it back in the freezer, the liquid becomes solid again. So that's a good thing to remember too. If it's a physical change, the change in a phase is reversible. It can go back and forth. Not so easy with chemical changes. A physical change could also involve dissolving one substance into another or separating out dissolved substances. So for example, if you remember how we gathered salt, where you just dry out salt water and what's left behind is salt, that is a physical change. The molecular structure of the water and salt don't change. You're just separating out the salt that has been dissolved in water. And you're doing that by allowing the water to evaporate, and that leaves only the salt behind. The same is true for mud dissolved in water. You can separate the two by filtering the mixture through a medium, such as a fine cloth or filter paper. Now watch this clip about physical and chemical changes for a quick recap of this topic. I will let you watch that another time, or I'll just upload it separately. Whatever works for us. But we'll move on and ask some questions. Hard water contains calcium and magnesium, which undergo oxidation and clogs water pipes. So, which statement best describes this change as a chemical change? Not dissolved in water, that's a physical change. Evaporate or on contact with the walls of the pipe. So evaporation or dissolving, those are physical changes. But this, forming a precipitate of their respective oxides, that is an important cue of a chemical change. Okay, so now we're organizing again. Sort these examples of change as either a physical change or a chemical change. Leaves turning yellow in autumn, coals burning to ashes, coals burning to ash. Thought is chemical. Lighting an electric bulb. Silver turning black when exposed to air. Sugar dissolving in water. Burning sugar cube. Distilling salt water to separate salt from water. It's physical. Wax solidifying when allowed to cool. It's physical. Okay, so let's see. Whew. Nice. All right, so now we're summarizing everything. Every substance has certain physical and chemical properties that make it unique. In this lesson, we explored these properties and learned how to differentiate between a physical change and a chemical change in a substance. The physical properties of a substance can be observed and measured without altering its molecular structure. Color, texture, melting, boiling point, conductivity, and malleability are some of the physical properties of a substance. The chemical properties of a substance determine how it reacts with other substances. Chemical properties of a substance include its pH value, how it reacts with oxygen, acids, bases, and water. Changes that occur in substances can be categorized as either physical or chemical. Physical changes involve the following: breaking, shaping, or reforming, a change in state or phase, dissolving one substance into another, separating dissolved substances. Chemical changes involve changing the molecular structure of one or more substances. 3 observable cues that a change is a chemical change include transfer of energy, change in structure, a new observable product. So either you see bubbling, a gas is bubbling out, or a precipitate is forming. Now that you've learned to identify, you can go back and take that quiz and see how many more correct answers you can get. But that's it for physical changes and chemical changes. If you have any questions or you're still confused between a physical change and a chemical change, let me know. Email me, message me in Canvas, and I will help you understand this as much as I can. But until next time, have a great day slash rest of your week, and I will see you all next time. Bye-bye.